Raindrops fall, rivers rise, paths one clear now, water hides. We swim not through waves but through time, seeking the moment when paths align. Imagine an island, a grid of heights and depths. The rain begins to pour, the water climbs higher, and every second that passes changes what we can reach. Somewhere on that grid lies our destination, a point of safety. But the question is, how long must we wait before we can swim there? In this problem, we dive into the heart of an algorithm that teaches us patience, precision, and persistence as we learn to swim in rising water. Let's start with the core idea of the problem. We are given an n by n matrix called grid, where each cell represents the elevation of the land at that point. As it begins to rain, the water level gradually rises. At any given time t, all cells with elevation less than or equal to t are underwater, which means they are traversal. We begin at the top left corner of the grid, that's position 0, 0. Our goal is to reach the bottom right corner, that is n-1, n-1. We can move up, down, left or right, but only through cells that are submerged or equal to the current water level. The challenge is to determine the minimum time t at which it becomes possible to reach the destination. In other words, how long must we wait before there exists a connected path from the top left to the bottom right cell? For example, if the grid is 0, 2, 1, 3, we find that the answer is 3. It means we must wait until the water level rises to height 3 before the path becomes connected. The intuition behind this problem lies in understanding how the flood progresses. As water rises, more and more cells become accessible. At first, only the lowest elevations are available, but as time increases, paths open up through higher ground. Our goal is to minimize distance or even time directly, but to minimize the maximum elevation we have to pass through on our path. We can think of it as finding the safest route, one that doesn't force us to climb to very high terrain early. This idea is very simple to Dijkstra's algorithm, which finds the shortest path in a weighted graph. The only difference is in Dijkstra's we minimize the sum of distances, while here we minimize the highest elevation encountered along the way. So instead of adding up costs, we care about the worst obstacle in our journey, and we try to make that obstacle as small as possible. Let's walk through the algorithmic approach to solving this. We will use a priority queue or a main heap, which helps us always choose the cell with the lowest elevation accessible at each step. Here's how it works. In step 1, we start from the left top cell and push it into the priority queue with its elevation. From there, at every step, we take the cell with the smallest elevation value from the heap. Each time we move to a new cell, we record the maximum elevation seen so far, because that's how high the water needs to rise for us to have reached that point. The moment we reach the bottom right cell, that recorded maximum elevation becomes our answer, the minimum time required to swim across the grid. This method is both efficient and intuitive. The time complexity is big of n square log n, since each cell can enter and leave the priority queue once, and the space complexity is big of n square for tracking visited cells. Let's now translate that logic into C++ code. We begin by including the standard libraries for vectors, queues, and utility functions. We define our solution class and our main function, swim in water. Inside it, we store the grid size n and define the possible directions of movement up, down, left, and right. We then initialize a main heap represented by a priority queue. Each element in the queue stores 3 pieces of data: the elevation, the row index, and the column index of a cell. We push the starting point 0, 0 into the heap with its elevation value, and we also mark this cell as visited, so we don't revisit it during the traversal. Next, we move into the main traversal loop. While the priority queue is not empty, we pop the cell with the smallest elevation value. For each popped cell, we compare its elevation with our running maximum res. This value res always represents the highest elevation we have seen so far on our path. If at any point we reach the bottom right cell, that is n-1, n-1, we can immediately return res, because by then the water level has risen just enough to make that route possible. This approach guarantees that we find the earliest possible time we can reach the goal. Finally, from our current cell, we explore all 4 possible neighboring cells. For each neighbor, we first check if it lies within the boundaries of the grid and hasn't been visited yet. If it's valid, we mark it as visited and push it into the priority queue with its elevation value. This ensures that in the next iterations, we will continue expanding through the lowest available elevations first, gradually forming the path of least resistance as the water level rises. When all reachable cells have been processed, our result represents the minimum elevation, or equivalently the minimum time t required to reach the goal. Let's walk through a concrete example to see how this logic works. Suppose we have a grid 0, 2, 1, 3. At time t equals to 0, we start at cell 0, 0 with elevation 0. None of the neighboring cells are accessible yet because their elevations are higher than the water level. As the water level rises to t equals to 1, we can now move down to cell 1, 0 with elevation 1. But we still can't move to the destination since 1, 1 has elevation 3. Finally, at t equals to 3, both 1, 0 and 1, 1 are submerged or equally to the water level. That means the path from 0, 0 to 1, 1 is now fully traversable. Hence, the minimum time required to reach the destination is 3. This example perfectly demonstrates how the water level correlates with the maximum elevation encountered along the optimal path. Now let's briefly discuss another possible approach. We can also solve this problem using binary search combined with BFS or TFS. In this approach, we pick a possible time t, meaning a possible water level, and perform a breadth first search to check whether it's possible to reach the destination when all cells with elevation less than or equals to t are allowed. If it's possible, we try a smaller t. If not, we increase it. This continues until we find the smallest t that allows traversal. While this method works and is easier to reason about conceptually, it tends to be slower with a time complexity of big O n square log n square due to repeated BFS calls. The priority queue method remains more optimal and elegant for this problem. Let's wrap up with some reflections on what we have learned. Swimming in rising water is more than a grid traversal problem. It's a beautiful example of transforming a physical scenario into a mathematical model. We reframed a natural event, the rising of water, as a minimax pathfinding problem. Using a priority queue, we simulated how the water gradually connects areas of the island, ensuring that at every step we took the lowest risk, lowest elevation move possible. The result was both efficient and intuitive, demonstrating the power of algorithmic thinking to solve real-world like dynamic problems. And perhaps the deeper message is this: no matter how high the water rises, there's always a path forward if we rise just high enough to make it. Thank you for your attention.